So we talked briefly about these two words last week, just in passing, but haven't defined them, and that's vector and scalar. But we discussed the concepts of displacement and distance, which are examples of vectors and scalars. So today we're going to dig into it a little bit more in detail, define both words, give you more examples, and then expand from there into some new ones today, specifically velocity and speed. So vectors versus scalars. We've talked about distance and displacement is the example of a vector and distance is the example of a scalar. But a vector is a number or a value that has a numerical magnitude. Magnitude just means numerical value. So it has a size, a numerical value. And then it also has direction like north, south, east, west, forward, backward, up, down, something like that. A scalar value is one that has a numerical amount to it, a magnitude, but the direction is either irrelevant or impossible to define. And so scalar numbers only have numerical value. Vectors have both numerical value and direction. And so that word magnitude really just means size, which is referring to having some sort of numerical value. Now, the way that we show the magnitude and direction together is to give vector numbers both the number value and a plus or minus sign. So vectors can be positive or negative because if they're going north or forward or east or right, they're considered positive directions. If you think about the coordinate plane, the y-axis and the x-axis, going up or north is positive, going east or right is positive. And then if you think about that same coordinate axis, going left or west would be negative, going down or south would be negative. So we use that same sort of coordinate plane logic to figure out whether the direction be considered positive or negative. And we can use the words. You could just say it is 30 miles north. So you could give it in word direction, but often we just give it a plus or minus sign to indicate the direction for vectors. Scalars, because we're not worried about the direction, we think about them as absolute values. They'll always be positives. And we talked about two examples last week, displacement and distance. And we even said displacement could be positive or negative and showed you some examples of that. And we said distance can't be because it's just a scalar value. It's just a length measurement regardless of path with no direction included. So can someone refresh our memory, just unmute and tell us again, how are displacement and distance different?
Displacement is kind of like a straight line from point A to point B, but distance is like the amount you travel.
Good. So we're talking about path length, the amount you travel for distance, and displacements is just in a straight line. And that fact that it's in a straight line helps us understand why we can give it a direction. If I'm going from point A to point B, I can draw a line that connects them. And if there's only one line, it points in one direction. And that one direction would be what we would clarify in terms of the vector. For distance, it could be that it's the same. Displacement and distance might be the same value. We just wouldn't give any direction for distance because it's sort of irrelevant. But if the path is wandering or meandering, then the distance and displacement will probably be very different. Some other examples too that we're going to talk about today are velocity and speed. So we often use velocity and speed in common language to be the same thing. And in terms of their numerical value or their magnitude, often they are. If the object is moving in a straight line, generally speaking, the size of the number, the magnitude of the number is going to be the same. But for a velocity, we also need to indicate direction because it's considered a vector. And for a speed, since it's a scalar, we don't care about the direction at all. Now, we're going to define each of these a little bit more clearly coming forward, but I just wanted to give you another example of two words that kind of go together, and they're going to be the focus of today's lesson, where one is the vector version and one is the scalar version. And displacement and distance are like that for measuring how far something goes. Velocity and speed are like that for measuring how fast something goes. Two more words that we'll use that have a connection like this, where one is a vector quantity and the other is scalar, are mass and weight. And we won't be looking at these in this unit. In fact, it's a couple units down the road when we get into forces, but mass is just how much matter is present. So if you've had a chemistry class before, you probably learned that mass is the amount of matter present in an object. And so the amount of kilograms is not directional. We wouldn't say that my mass is 85 kilograms north. That doesn't make sense. It's just, that's how much matter there is, just 85 kilograms. But weight is actually a force that is analyzing how the gravitational pull of the Earth impacts our mass. And so weight would always be downward towards the center of the Earth. And so weight is directional. And while the displacement and the distance could be the same if it's in a straight line, and velocity and speed could be the same if it's in a straight line movement, the only difference in those cases would be just saying the direction for displacement and velocity and not worrying about it for distance and speed. For weight and mass, those can't be the same because weight is dependent on both the mass of the object and the gravitational force, whereas the mass is only one element of that. So those can't be the same if there's any gravity present. The last example isn't a pair. So displacement and distance kind of go together, velocity and speed go together, weight and mass go together. This last one, though, they don't go together, but they are two words we're going to look at in this course. One is acceleration, and that is going to be the focus of our next unit. So just looking ahead at the schedule, today we're going to have this section of notes, and then on Thursday we're going to have another section of notes, the last part of the Unit 2 notes. And then next Monday we'll be reviewing, and then next Thursday we'll be actually taking a test in some manner over Unit 2. Now, I'm not exactly sure how that test will look right now because normally I have questions that are from College Board that are secured questions. And so I can't put those online. I can't post them in an email. I can't have any access to them outside of where they could be acquired by other people or posted by other people. So I'm having to think about how I can recreate that test without using those secured questions, but still keep it more towards the AP level. So I'm still wrestling with how to make that work next Thursday, but I wanted you to be aware that that's just a little over a week away. But acceleration will be the focus of the unit after. So once we take that test next Thursday, then we'll be digging into the concept of acceleration for a couple weeks. And that concept is when we have an object that is changing its velocity. Usually we think about it either speeding up or slowing down, but we'll talk about that more in the next unit. Time is a word that we're going to focus in on today, and it doesn't necessarily match with acceleration. It's just another scalar that's important to understand. And you all know what time means. We measure time in seconds, but so we wouldn't say time is directional. Time just moves forward in terms of progression. And so we don't have like 30 seconds south. It doesn't, we could do that if we're talking about degrees in seconds, but not in terms of time. And so we have time without any sort of direction. So those are the key words that help us understand the difference between vectors and scalars. Any questions on that? That's quite a few keywords there today to begin. All right, the next few slides will be a little bit quicker, just kind of passing through some conversation. So what time is it? Like distance, time is fundamental. Everyone kind of knows what it means, but it can be a little hard to define. We always feel like we want to use the word time to define time because it's so common, it's so fundamental, it's so understood. So usually the way we try to define it or understand time is by comparing, like comparing to this moment into a later moment or this moment into a past moment. We figure out how much time passed between those two instances. And so just like distances, we usually do comparisons to understand time. So for example, we might say the second hand on my watch went around one time while I was running around the track. And our conclusion then would be that that run around the track took 60 seconds. So we must have been running pretty fast. When we compare the time between two events, we are actually measuring time. So we're not really defining it, we're measuring it. But by measuring it, it gives us a value that we can work with and use in computation. And so just like distance, we measure it, and we usually talk about measurements of distance more than we talk about the meaning of distance. And same with time. We usually just talk about measurements of time rather than the meaning of time. We sort of instinctually, based on our life experiences, understand the concept of distance and time, so we focus more on the measuring of those two fundamental concepts in our class. Now, when we do measure time, we use seconds as our standard, and the variable that we use is lowercase t. We can use a capital T for temperature, and we can also use a capital T for a concept called period, but we use lowercase t for time. And as we said, the unit is seconds. I'm not going to show this video. Interesting, it's called Minute Physics, and we're talking about time. But for the sake of time, I'm not going to actually show it in class. But it is on Access if you're really curious and want to see it. It does just kind of take about 1 minute and 45 seconds and give an interesting conversation about how we often mix time and distance. Like if I said, well, how long does it take to get from my house to Oaks? I would say 15 minutes. And I just answered, you said, how long does it take? And I said 15 minutes. But if you said, how far is Oaks from my house? I'd probably still say 15 minutes. I don't actually know how many miles it is, but I know it takes me about 15 minutes to get there. So often we answer how far something is in time. And that's what this video is about. So if you're curious, you can go to Topics Unit 2. It's down at the bottom of the links, and it just has this link to that. So you're welcome to watch that if you're interested. But let's talk a little bit more about how we measure time and 2 different ways that we could measure time, or at least not ways to measure it, but 2 ways to think about our measured time values. So let's say we had a book that dropped to the table, and then after it hit the table, we slid it to another place on the table. So we could be thinking about time passing in these instances. So I might start the stopwatch when I drop the book, and then we could see how much time elapsed from when I dropped it to when it hit the table. Or I could measure how long it took for me to slide the book across the table, how much time elapsed while I was sliding the book across the table. Or I could just stop the clock at any point in time to see what time was it when the book hit. So I could start the timer when I dropped the book and then stop it right when the book hits the table, and then I would know exactly when it hit. So the point is, occasionally we're trying to think about how much time passed, and occasionally we're trying to figure out what is the clock reading or what is the point in time when something happened. And so both of those things could be important. So here's a couple more definitions for you. I'll just give you a few seconds to kind of read it, jot something down in your notes, and then we'll discuss it. So occasionally it might be more helpful for us to know the instantaneous time. What was the clock reading right when something happened? That may be important. And so sometimes you'll be asked to determine that. Most often we're more concerned about the amount of time that passed or how many seconds passed, the time elapsed between 2 events. And while they're both important, like I said, the time interval, the elapsed time, is actually the more common thing that we're asked to figure out. In fact, in our next unit, again, starting after our test next week, we're going to be looking at a lot of kinematics equations where we have delta t. What does that delta mean again?
Change.
Change, yeah. So that triangle, that delta symbol means change in time. And a lot of the equations have delta t in them. And yet occasionally they won't want the delta t, they'll actually want the final time. And so it's important to understand, just like the change in position is the final position minus initial position, the change in time is final time minus initial time. So just a quick overview of the difference between these. You might be asked to analyze either one. All right, now let's talk about speed. So we mentioned in a couple slides back that speed is an example of a scalar. We don't care about the direction of an object when we're referring to its speed. We just want to know what is the ratio of the distance that it traveled compared to the time it took to travel that distance. So we've got a word definition there at the top. We've got more of an equation definition there in the middle, still a word equation. And then right underneath that, a more traditional formula, speed equals distance over change in time. And occasionally this little delta here, sometimes that will be missing. So you sometimes will just see it as d over t. And the reason they sometimes leave the triangle off is because when we're making measurements, we typically start the stopwatch and just say, okay, go. And we start the stopwatch, and then when it's over, we stop it. And so the elapsed time is the instantaneous time at the end. And so sometimes they don't put the delta in the equation. I've put it here on this slide for you to see, just because it is technically an elapsed time. You can't travel distance if no time elapsed. So there has to be some elapsed time, even if it's a very small amount. And speed is a ratio. It's not a fundamental concept like distance or time are. Distance is just something that we understand fundamentally, but speed is a ratio of distance to time. And a lot of the things we learn in this class will be more of a ratio. And so just starting to introduce that idea. Questions about the idea of speed or the concept of speed? Moving forward, the units for speed are meters per second, and it's pretty obvious if you just substitute the unit in for distance as meters. If you just substitute the unit in for time, it is seconds. So meters per second makes sense. We would read it as meters per second, but those are the units. The standard units we use for those two individual sort of fundamental concepts are the same units we use in the ratio. All right, now we're going to go back to our example with Dorothy and Toto that we talked about last week. And you may remember we were trying to figure out who went further, Dorothy or Toto. And we said, actually, it depends on how you define the word farther. Are you meaning farther in terms of path length, or are you meaning farther in terms of how far they are from where they started? And so that's where we picked up on the concept of distance versus displacement, that the word farther is pretty vague, but the way physics has defined distance and displacement, it's very specific. The distance is the path. The displacement is straight from point A to point B. So now let's think about the same scenario with Dorothy and Toto, but let's try to figure out who moved faster. So in this situation, Dorothy starts here and moves along the same path we saw before, and it takes her 9 seconds. Toto starts here and moves in this circuitous path all over the place, ends up where he did before, and it also takes Toto 9 seconds. So given this information, go ahead and put it in the chat. Who was moving faster? Okay, I'm seeing a lot of votes for Toto. Jackson specifically said Toto had a faster speed. So Jackson, is there a thought behind that, or just a factual statement?
It's because like distance is like the distance she traveled, and then like displacement would be velocity. So if we're talking about velocity, it would be Dorothy, right?
Good. Yeah. So if we're thinking about how fast something moves, that's a ratio. And if we're thinking about specifically the ratio we just defined as speed, then Toto's faster because Toto had the greater speed. Toto covered a larger path length distance in 9 seconds. But if we're talking about faster as the displacement compared to time, as we said last time, Dorothy starts here and ends up pretty far from where she started. Toto starts here and ends up closer to where Toto started. So in terms of displacement, Dorothy's displacement is much longer in 9 seconds, and Toto's displacement is shorter in 9 seconds. So if we're thinking of distance versus time, Toto's faster. If we're thinking about displacement versus time, Dorothy's faster. So just like the word farther is kind of too vague to use in physics, we need to define it further, farther and further. This faster word is kind of the same way. If we just say faster, we need to specify, well, do you mean the distance to time ratio, or do you mean the displacement to time ratio? So let's define them. A couple more words here for you. Let me just leave this up for you for a minute or so, and you can read it, think about it, put it in your own words, and then we'll discuss it in a minute or two. All right, so we've just defined speed in the previous couple of slides, thinking through the fact that it's distance versus time. But because distance is a scalar and directionless, we also need to think about its counterpart, displacement, which is a vector including direction. So if we need to think about how fast something's moving and the direction is important, we should think about the displacement compared to the elapsed time. And we call that velocity. So like we saw on the previous slide of vectors versus scalars, velocity and speed kind of go hand in hand, but they're technically a bit different. Speed is the distance in time, with distance being a scalar, and velocity is the displacement compared to time. And displacement is a vector, so that makes velocity a vector. And because we can give direction for the displacement and should give direction for the displacement, we should also give direction for the velocity. Now you can see the equations here. Speed equals distance over delta t, distance in the changing time or elapsed time, and velocity equals change in position or displacement over change in t or the elapsed time. That is typically what we're going to be thinking about. And in today's assignment with worksheet 3, the questions are focusing in on the averages, and almost all the questions in your positive physics assignment that you've been working on also ask you to think about averages. And so that is an important part for what we're doing here in this unit. In the next unit, so I'm starting to foreshadow it, and I've talked to you before about how I like to spiral concepts. So I'm even starting to tell you some words and some basic ideas about concepts coming in a future unit so that you've heard them before. So in the next unit we cover, we're going to be focusing a little bit less on the average velocities and average speeds, and a little bit more on instantaneous velocities and speeds. What is the speed at a particular instant in time, a particular point in time? And so I want you today to just start think about the fact that while we're focusing on averages right now, there is a way to measure what is the speed right now. So an example would be thinking through, like, if you're driving by a policeman with a radar gun, they check your speed at that instant. Now, that doesn't mean you were driving that speed the whole time you were driving. Your average speed may have been very different, but the speed at that instant was what the gun says. So there is a difference, and they can both have important meaning. Right now we're focused on averages, but later we'll be focused on instantaneous. Any questions before we move on from these definitions? All right. So the last little bit, we've talked about how displacement and distance, we had to kind of clarify further or farther. What do we mean by that? Is it scalar or vector form of that? And then faster, we had to also think about, for faster, we need to clarify, are we talking about the scalar or vector form of that? Well, there's one more concept we have to keep in mind when we're talking about movement. In this question, we've gone from the classic Wizard of Oz with Dorothy and Toto to the classic tortoise and the hare. And in this one, the question is who's moving faster, but the scenario is a bit different. The hare, the rabbit, is running along the ground, and the tortoise is walking along a train, but the train happens to be moving on a track. So what do you think about this one? Go ahead and in the chat. Who is moving faster in this scenario? Okay, a lot of people, I think everybody so far saying the turtle, the tortoise. So if we're saying the tortoise is faster, and that's a logical conclusion, what we really mean is the tortoise is faster relative to the ground. Relative to the ground, how fast is the tortoise moving?
30.1 meters per second.
Good, and that's a lot faster than the rabbit, who's only moving 5 meters per second relative to the ground. But, or we could even say relative to one another. The turtle is moving fast relative to the hare. If we saw them going side by side, the tortoise would be going faster than the hare because it's on the train. Now, if we rephrased it and said, who's moving faster relative to the surface they're on, then it's the hare, because relative to the surface that the rabbit is on, it's 5 meters per second, and relative to the surface that the tortoise is on, it's only 0.1 meter per second. So we have to have an understanding about our frame of reference. And that's going to come up again in a later unit as well, but it's important now too. When we're talking about faster or slower, we have to give a frame of reference. So let me give you another example. You've probably, most of you experienced this before. Have you ever been sitting in a car and you're still, like you're parked, and you know you're parked, but the car beside you moves and you kind of see it moving out of the corner of your eye and you think you're moving, right? I mean, sometimes it like startles you. You feel like you're moving and you know you're not. But that frame of reference, that little perspective makes it almost feel like it's moving. Or maybe you've been on a ride at an amusement park like Disney World or something, and you're moving on this really slow moving trolley that's just going flat on the ground at, 5 feet per second or something, pretty slow. But there's these videos flying around and you feel like you're in an airplane or you feel like you're riding a roller coaster, and it actually can make your stomach feel like you're riding on the hills sometimes because of the perspective around you. But when you look down at the ground, you're barely moving. And so our frame of reference is important. A lot of times there'll be questions from College Board about frame of reference similar to this. I'll give you an example here. If you're driving down the highway and you look over and the car beside you seems to be motionless, what does that tell you about that car?
It's
Lily?
going at the same speed as you.
Yeah. And so compared to you, if you're the reference frame, it appears as if that car's not moving. But if you're moving, it has to be moving, right? And so its speed relative to you is 0. It has the same speed. It's no different than your speed. But relative to the ground, you're both going the same speed. If you looked over and you saw a car that appears to be going backward, and you know that's impossible, what does that tell you about that other car's movement?
It's going slower.
It's going slower than you are. And so the frame of reference is important. If we're not comparing it to the background, if we're just comparing it to our own position, that frame of reference can be different than the values we determine can be different than if we're comparing it to the ground or to some other reference frame. So that's going to be an important aspect as well.
I have a quick question.
Sure.
So when we say this turtle, relative to the ground, like what is the actual speed? It's like 30 or 30.
It'd be 30.1 meters per second relative to the ground.
30.1. Oh, okay. Why would you say 30.1? Shouldn't it be like 30?
Well, the train is moving 30 and the turtle is moving 0.1 on their own. So compared to the ground, the turtle itself is moving 30.1 meters per second compared to the ground. Now, eventually the turtle is going to reach the end of the train and will have to stop. But as long as it can keep moving forward, it's actually covering more ground than the train is. Just a little bit more, but it's actually moving forward a little bit faster compared to the ground than the train is.
Oh, okay. Okay.
All right. Another frame of reference scenario is like if you've ever been in a car and you're tossing a ball up and down. To you, the ball just feels like it's moving straight, right? It just feels like it's going straight up and straight down, straight up and straight down. But if you were driving by somebody and they were standing on the sidewalk and they saw you drive by, the ball isn't going straight up and down. You and the ball both are going, the ball's going up and over and down, and you're going straight across. So depending again on frame of reference, someone standing on the sidewalk has a different frame of reference and sees the motion differently than you do actually in the same car. Everybody in the car sees it the same way, but someone outside the car would see it different. Other questions about frame of reference? In the next unit, we'll actually watch a kind of a clever video back from the 50s, I think, 50s or 60s about that. But I wanted to introduce it now because it is still relevant for this unit as well. All right, so let's wrap this up with some questions. Just put your answers in the chat and we'll see how you do on these. I'll read it out for you. A car travels at a constant speed of 10 meters per second. This means that the car, A, increases its speed by 10 meters every second. B, decreases its speed by 10 meters every second. C, moves with an acceleration of 10 meters every second. Or D, moves 10 meters every second. Good, I'm seeing a lot of, I think everybody choosing D. Speed has nothing to do with increasing or decreasing. It's just how many meters is the object covering per second. All right. Number 9, a rabbit runs a distance of 60 meters in 20 seconds. What's the speed of the rabbit? Good, 3 meters per second. So we're just using that relationship. Speed is distance over time. So distance is 60 meters and time is 20 seconds. So the average speed is 3 meters per second. Now, just knowing how rabbits run, there's probably very little likelihood that this speed is the same as the velocity, because rabbits often run in a very zigzag manner. And so probably if they're covering 60 meters on their path, their velocity is probably a bit different because they don't generally run in straight lines for very long. An airplane on a runway can cover 500 meters in 10 seconds. What is the airplane's average speed? Good. So again, distance over time, 500 meters divided by 10 seconds, average speed of 500 meters per second. For the airplane going down a runway, it is probably actually going in a pretty straight line, hopefully. And if it's going in a straight line, its speed and velocity's numerical value would be the same. The only difference would be for the velocity, we would just need to add a direction. So for something like an airplane, the speed and the velocity are probably the same magnitude. All right, a car travels at a speed of 40 meters per second for 4 seconds. What's the distance traveled by the car? Okay, good. So we have to think about our equation here. For distance, if speed is distance over time, distance would be speed multiplied by time. So 40 meters per second times 4 seconds gives us 160 meters. And we can see meters over seconds multiplied by seconds. The seconds would cancel and give us meters. So we can actually check the dimensional correctness of our problem as well to make sure that we've solved for the correct thing and that our units make sense. It says, what is the distance? Meters is appropriate for distance, so it looks like we've probably done this correct. All right, you travel at a speed of 8 meters per second for 6 seconds. What distance have you moved? All right, good. So same as before, the speed multiplied by the time cancels seconds and tells us we would have moved 48 meters. 2 questions to wrap it up here. You travel at a constant speed of 6 meters per second. How much time does it take you to travel a distance of 120 meters? In this case, we're thinking if speed is distance over time, time would be distance over speed, just rewriting the algebra. And so 120 meters divided by 60 meters per second, the meters cancel and give us 20 seconds. Now on AP, the way they wouldn't normally give you a question quite this simple on the final exam, but the way they normally grade it is you have to show one of these equations, and then you have to show the substitution to earn full credit. And so I do want you to get into the habit of that, even on simple questions like these that you can do in your head. You do need to show the equation, then you need to substitute. All right, last one. You travel at a constant speed of 5 meters per second. How much time does it take you to travel a distance of 150 meters? Very good. Same scenario. Distance over speed, 150 divided by 5 gives us 30 seconds. Any questions? Those are just similar to what you're doing in some of the positive physics questions, this sort of mental math, making sure you're processing it quickly and correctly. Anything from you guys you want to ask about? All right. So we're going to take about 25 minutes and have you work in breakout groups on worksheet 3. So if you go to Axis and under the Topics tab, you'll be able to find worksheet 3 both in a document form and a PDF form. So you can choose which file type you like. And I showed this one to you last week, so some of you probably have already started it. If you haven't, no worries. That's the goal today. My hope is in this 25 minutes that by the end, you will all be done with the first 3 pages. If you got started early, then you might actually finish it in class today. But that's depends on how much you've been able to do ahead of time, if any. So hopefully you'll find the worksheet. As you're working, obviously working together, helping each other out, comparing answers, I'll hop around from room to room and see if you have questions. You can click on the button at the bottom of the breakout to call me in for help. And then after 25 minutes, we'll come back together in the main class and discuss what you've come up with and kind of let you check your answers as we have that discussion. Any questions about the procedure, what we're doing? All right. So find worksheet 3. Let me send you off into your breakout rooms here. All right. All right, I think everybody is back in the main room. So let's go ahead and jump in. I'm going to show the key and talk through some of the questions. If you have questions about anything we cover, just unmute and jump right in. Make sure you get all your questions answered. All right, so if we look at the first question, it talks about Robin roller skating down a marked sidewalk and being observed and timed, and they give you some data and you graph it, and you should see a linear relationship with this first scenario. Part B says explain how you can use the graph to determine how far he was from the origin at 6 seconds. So if you go up from the 6, you can see that somewhere between 20 and 25, so around 22, 23 meters. There'll be some plus or minus estimation there, but around 22 meters, you're just using the graph to determine that position relative to the origin. And you can see from the graph that he didn't start at the origin. If this is the 0 mark on the ground, the timer didn't start until he was already at 10 meters from that 0 mark, and then just kept moving further and further away. Part C, write a mathematical expression that describes the skater's motion. So we've got y equals 2x plus 10 is just the raw sort of equation without properly correctly writing it as a model. And then this is a more acceptable model with complete units. And now let me actually though see if I can, whoops. Is it gonna let me drag it? Let's undo that. Let's put it down below. I did want to show you that you can put, instead of position X if you choose, and instead of time, because I've had a few students ask, can we just write it that way? And so that is fine as well. If you'd rather write it with just X and T, X for position and T for time.
For that expression, do we have to include the correct number of significant digits for full credit?
I probably wouldn't take off points yet for that, but eventually you would need to do that. So it would be a good habit to try to go ahead and get used to doing.
Thank you.
Yeah. All right. And then D, was her speed constant over the entire interval, and how do you know? Since the slope was constant, that means that the skater's speed was also constant. And so that's how we would know that Robin was moving at the same rate the whole time. Questions? All right, let's move on to page 2. For page 2, we've got a second trial. So this time it says they started the timer a bit sooner. So instead of starting it when Robin was at the 10-meter mark, they've started it when Robin was down here at about the 4-meter mark. But when you plot these points, you can still see that the progress was linear in nature, still traveling the same distance every second. How far from the 0 position was the skater at 5 seconds? So if you go up at 5 seconds, this time it's about 18, 19, somewhere in that 17, 18, 19 range, somewhere between 15 and 20. And you could guesstimate it from this as well. It's going to be somewhere between 16 and 22. So around 19 meters would be that distance. And then part C, was the skater's speed constant? And if so, what was it? So you didn't necessarily have to write it as a full model this time. I just did just to show again what it would look like in this case. And you can see the speed is 3 meters per second in the model. And again, we know the slope is constant, and the slope tells us the speed. So with this one having a slope of 3 meters per second, in scenario 2, Robin is actually moving faster. D, in the first trial, the skater was further along at 2 seconds than he was in the second trial. Does this mean he was going faster? Explain your answer. So again, if we look here, started at 4. So after 2 seconds, he was just getting to the 10-meter mark. And then in this one, started at 10. So after 2 seconds, he was already about 14 meters out. So does it mean he's going faster? No, just started from a different position. In fact, he's going slower, because in the first one we saw the slope is only 2 meters per second. And this one we can see the slope is 3 meters per second. So the skater was not going slower in the second trial, just had a different starting position, different y-intercept graphically. Questions about anything on page 1 or 2? All right. On to 3. We've only got a couple minutes left, so we'll probably just start this. But in this one, I just want to talk a little bit about the graph in case you're not done with pages 3 and 4 yet, so you know you're on the right track. So in this scenario, we see that as you plot the points, it is not a straight line. It is not a linear relationship. So it appears that the movement of the skater is very irregular. And it doesn't look like it's parabolic in nature or a square root type of relationship or inverse. It looks like there was some stopping and starting. And so if it doesn't look like there was a consistent movement, you can just graph almost like a connecting the dots to show the different segments. So in this first segment, you can see from 0 to 4 seconds, he seemed to be going at a steady pace till he reached the 4-meter mark, and then no movement. And then going back towards the 2-meter mark over a 4-second span, and then pausing again, and then going forward again, a distance of 6 meters in 4 seconds over that last segment of time. So this one's a little bit different in the scenario in that it's not steady. What do you think is happening during the time interval of 4 to 6 seconds? Well, the position stays at 4 meters the whole time. So apparently Robin appears to not be moving in that time frame. And then C, what do you think is happening during the time interval from 6 to 10 seconds? From 6 to 10, he's going from 4-meter position to 2-meter position. So apparently is moving backward during that span of time. So hopefully that makes sense, and hopefully whoever's using the weed eater outside my house is not distracting you too much. Hopefully you can still hear me okay. But I'll just show you the answers for D and E so you can kind of check your work if you made it that far. But we will pick up with letter D next time, and hopefully there won't be someone making a lot of racket outside my window. Couple reminders though before you go. Don't forget Positive Physics Unit 1 work is due tonight. Your completion grade is what you'll earn. And then 2, don't forget you need to be registering for the AP exam soon. Deadline's October 1st. And last, if you're doing a retest of quiz 1, then make sure you're ready to do that today at 3:30, tomorrow at 3:30, or Wednesday at 1:30. All right. If you have questions, you can stay online. I'll be happy to answer them. If not, I will see you on Thursday or in a retake session.
Thank you.
Thank you.
Have a good day.
Thank you.
I just have a quick, not a quick question, because I encountered something.
Okay. Haley, do you have a quick question?
Yeah, I do. So do we have to finish this worksheet now, or are we working on it again in class? Because
We'll just,
I was on the back page and I was kind of confused.
yeah, we're gonna check the rest of it the next time we meet.
Okay.